can start. Very welcome to the 4th week of Introduction to Data Science. Let me start with some notices. Thanks to all those who participate in the competition, they will get extra points in the exam, and thanks to all those who wrote in the issues. So, given that maybe I see new faces, you all know that there is the GitHub website of the book. You all know there is, okay. Then you know that there are the issues, and the issues finally I've answered to all of them. Right. So maybe tomorrow we will do another competition here. Please also try to participate as much as possible, because I will acknowledge your participation during the exam. What I want to discriminate, and once again, I want to understand who participates in the activities of the course. That's my main goal. Okay, and this, everything you do in GitHub remains until the end of the world. Okay? Unless you do something, unless you yourself decide to remove all your history, but that remains. So all that you say, every comment, every reaction remains and is visible to all the world. Of course, during the exam, do not forget to write your GitHub nickname. Do remember it. First thing, open a new file, write your GitHub nickname, and mention if you won a competition, mention everything, because I have to read. Of course, I will check, but it is important that you mention all these things. Once again, sorry me repeating that, but you can be notified about everything. So you do watch and then all activity. So wherever you are in the world, if there is a competition, you receive an email and then you can participate. Right? So I keep repeating things, but I want to make sure that all these things are fine and well understood. Now, next Thursday, there will be the seminar of Professor Aldo Corbellini about GitHub for software development. If you want to participate, let us know. Unfortunately, here, I don't know, and also Professor Corbellini was a bit disappointed because he saw that just 7 persons, list of people, here there are 7 persons who put their name in the participation. This is an additional thing that is an additional opportunity. Take advantage of it. It is obscure to me how some persons did not put yet their nickname. It is a mystery to me. Mysterious. There are certain things in life that are really mysterious for me. Now, students who didn't have the MATLAB license, I've written a series of emails. Now they have received the MATLAB license. So each of you, now enrolled or not, should have the MATLAB license. Do confirm that this is the case. You see that with the University of Parma, maybe things sometimes are late. But it's better that things are done, but we are not person who say that, okay, everything will be ready from the first day. No, things are going in the right direction. Right. So those who already had the UniPR email, but were unable to install MATLAB, please let me know, because I've been told that they want to know why. Because everyone who has the UniPR email should be entitled to download the full version. Right. Okay. If there is no other thing, we can keep going with the remaining part. I don't know if you have questions. Okay, now, yeah, please. Because otherwise people from internet cannot hear. Can you give her the microphone? It is better. Otherwise, people from internet cannot hear what you are asking.
Just a question. I don't have passcode, so the secretariat didn't give me access to like non-active, advanced students to like necessary materials. So I don't have any of them.
Okay, let me know. Okay, now you will give him. Yeah. You will give him your email address, and then he will collect the list of additional people for which the MATLAB license has to be given. So you give him your Gmail address or whatever, your email. Then within next week, you'll have the MATLAB license. Then when you'll be formally enrolled, okay, you'll have the UniPR address and everything's fine. Okay, so you see that I insist so much, but at the end of the day, okay. Okay, so, I keep insisting. So, therefore, once again, I encourage all of you to ask me things. Okay. Then, other questions. Your case has been solved with the Giapichelli website already last week. Right, everyone. Therefore, should be fine. So, no. It is not the problem of anyone. It is things, sometimes, also I was not aware how the system worked, so it was unclear for me as well. They were absolutely right, yes. In fact, we acted as beginners, but whatever, makes sense. Good morning. So, and you also have the MATLAB license, everything is fine?
I have 1 month free trial.
No. Yes. And then you should have, you have received an email from Mattworks saying that yesterday?
Okay. No, not yet. I haven't received it.
Okay. So let us check if she gave you your email address, because I've been told that all the people in the list should have received an email yesterday. Okay, so let us move on. What is his name? What is his name? What? Siv. Let us go. Right. Okay. Okay. I hope that you already have had a basic course on random variables, density, probability density distribution. Well, some of you already had, but the thing is that we have seen the frequency distribution, but the goal is to understand what is the theoretical distribution which generated the observed empirical distribution. So we have the empirical distribution, but the real distribution is known just by God. So we have to estimate. That's the issue. Now, the objective is for each distribution, we have to find out what is the data generating process, what is the cumulative distribution, what are the quantiles, and how to generate numbers from a particular distribution. So the basic concepts are density, how the probability is distributed over different values of a random variable. Here, basically, it represents the likelihood of observing a specific value or values inside a specific interval. On the other end, we had the CDF, cumulative distribution function, that the probability that the variable takes value less than or equal to x, right? So generally, the PDF of x is denoted with the lowercase letter, lowercase, right? On the other end, the CDF is this. And then we have the quantiles. For example, x 0.05, something like that. So the CDF is the probability that the distribution takes value less than or equal than x. The quantile is that you fix a particular probability on the left or on the right. And then, for example, you wanted to know what is the value that lives on the right, a probability, prefixed probability. For example, a probability of 0.95, right? That's the quantile, right? So, or you can fix x, and then you can ask, what is the y coordinate, the density? What is the probability of values smaller than x, smaller or equal to x? The CDF. On the other end, you fix this area, and then this area must be 0.95, and what is the x coordinate? You see the difference between the two, eh? Okay. With the quantiles, you fix the area, and then you wanted to find the x coordinate. On the other end, you fix the x coordinate, and then you wanted to find the density or the probability, then the random variable assumes value smaller than x. Smaller or equal in case of continuous distribution is exactly the same, because the probability that the random variable takes a particular value is 0. So probability in a random variable, continuous random variable, the probability that x continuous is equal to 3 is 0. For continuous random variables, we are talking about probabilities referred to a particular interval. Different is the situation if we have a discrete random variable. If the random variable is discrete, then you have the probability of observing, for example, 1, 2, 3, and then each value has a probability. Of course, it goes without saying that the sum of the probability is equal to 1, the discrete case, and the integral, or if you want, the integral of all the overall density is equal to 1. So this is the typical case of a discrete, this is the typical case of the continuous random variable. In this case, the area of a continuous random variable, the integral from minus infinity to plus infinity is equal to 1, right? And then the density can be negative? Absolutely not. It is a probability, and the probability by definition is cannot be smaller than 0, right? So let me say something about the CDF. So the CDF is monotonically non-decreasing. In case of a discrete random variable, it has steps. So it starts with 0, and then when x tends to infinity, then it goes to 1. And the density, you see, is discrete. Now, for a continuous random variable, therefore, this is the probability that x is smaller or equal than a. On the other end, this is the density. Okay, now, we have to estimate this density. We have to estimate the parameters of this density. And for a continuous random variable, in order to find the probability that the random variable assumes value in a particular interval, then you do the CDF of the upper extreme minus the CDF of the lower extreme. Okay, all these concepts are very familiar, isn't it? Tell me, because I have no idea. Okay, so in case of a normal distribution, you all have already seen the normal distribution, do you? Right. Now, let me show you now a dist tool. If you try dist tool in MATLAB, this is what you get. A graphical user interface. And it says which distribution you are going to see.
Is this because if you install it here,
No. This is pure MATLAB. This is pure MATLAB. This tool is a graphical user interface that lets you play with the different distribution, lets you understand what is the meaning of the parameters. For example, you see that you have indeed many distributions. So we start with the normal, and then CDF or PDF. This is the density, and this is the CDF, the cumulative distribution function. Of course, the cumulative distribution function, here it is for the standard normal. Mu is equal to 0 and sigma is equal to 1. So you see that, well, you can put here your mouse and then you find the probability. So the probability, yes, of course, goes from 0 to 1. When x tends to infinity, the probability is 0 plus. When x goes to plus infinity, the probability tends to 1 minus. Now, PDF. What is the meaning of this parameter mu? This parameter mu. If you change it, this is a location parameter. So, this is the effect of changing mu, you see? That is, the shape remains absolutely the same. The only one thing which changes is the location. Now, let us see on the other end the effect of sigma. If you increase sigma, of course, it becomes more and more spread. Right. Of course, if you decrease sigma with the lower bound maybe of 0.001, you see how the normal becomes very concentrated, you see. But the integral is 1, in all cases, there is no need to underline it. So the area is always 1. But this parameter has to do with the variability of the distribution. Right. So how do you estimate the location parameter of the normal distribution? With the arithmetic mean. How do you estimate the variance parameter of the normal distribution? With the standard deviation. Okay? Now, and mu is the mean of the distribution. So if you solve this integral, it's not the purpose of let you solve integrals, but if you solve this integral, then you find mu. If you solve the second moment here, if you solve this thing, you do find the sigma square. Right. So you see that the basic things to remember are PDF and CDF. And of course, for the normal distribution, the functions are norm PDF and norm CDF. Goes without saying. Okay? For example, what is in a standard normal the probability of having values smaller than 1.5, then it says mu and sigma. If mu and sigma are not specified, what do you assume? Of course, mu is equal to 0 and sigma is equal to 1, right? So therefore, this thing is absolutely equal to this one, right? 0 mean and variance is equal to 1. That's something which is very basic and standard. Now, okay, now let us draw the density and the CDF. So with this normal intro. With this file normal intro, then of course you do, every time you do source control pool in order to download all these files. So, normal intro is inside CH5 distributions. Okay, so all these are all the files that yesterday night I put on the web. I pushed on the web because my life is or I work during the night, or otherwise there are really too many things, and otherwise I do not survive. So my only one possibility is to do things after dinner, where everyone is much more. Otherwise, my phone always rings. Everyone comes with a particular request, so it is impossible. Now, you let us comment this code. You have a set of x coordinate, a column vector, then you define the mean and variance. Note that here I call mean is equal to 3. However, this is, let us say, very dangerous, because you see now I have defined, let me close all and clear all. Come on, go away. I've clicked on, okay. It takes some, okay. I've cleared all my variables in memory. So I've defined mean is equal to 3. But mean is also the name of a function. So if you do, for example, mean of 258, it works? Absolutely does not work. You see, because it says that mean appears to be both a function and a variable. Of course, you have this variable in memory which is called mean that conflicts with your call to function mean, which computes the arithmetic mean. And in fact, MATLAB says it to remove the variable mean from the workspace. So if you remove it from the workspace and then you do mean, okay, of course it works. This goes without saying. Keep in mind, but this is wanted just to show you this issue. Now, here you see that norm PDF now of X with a particular mean and particular sigma. And then you have YPDF CHK, which is the manual, so-called manual implementation, using the formula. So you, if you want, you try to do it, the manual implementation. And then there is an assert which checks that the two implementations are equal. So you do plotting XPDF, and then here in second subplot you do plot of the CDF. You see, the second column. You construct the CDF and the plot. Now, let us see. This is the output, okay? Now, you know what is the ESP number. You all know what is the ESP number. you see that here you have exp. You know this notation. Which number is exp? Yeah, you of course, you already know, but there are people, okay, of course, I mean, for example, you know what is number exp? Because you have to be able to read mathematics. So please, because there are certain things that are really obvious, but if no one has ever told you, you cannot know. So once again, you make me the favor asking and stopping me when you do not understand something. We all agree. This is an agreement that we must have. You stop me anytime there is a symbol that you do not understand. So for example, here there is exp. Exp is the exponential. Which number is exp? What is number exp? Try. What? One? No. But this is, I mean, also, but in Excel, if you do exp1, what do you get? You get 2.718, which is the natural basis of the logs per number, right? So, and then, but you also try it in MATLAB, exp1 or in Python or whatever, and there you get this number, right? Therefore, exp3 means this number raised to the third, right? Okay, that's the thing. And so here, when you do this implementation, you see exp of all these things. This is a vector, this is a scalar, this is a scalar. And then you see square, and then you see you raise each element to the square. You see, you do this element-wise thing. Right? And then this is multiplied by square root of pi times sigma. Of course, pi, everyone knows what is pi, do you? Okay. Yes, of course. But exp is another magic number. It is 2.718. So, so is it clear why here you do in the title, you do num to str? For the mean and variance. So this is the title that appears, density function normal 3-4. Because here you want to have something, so if you put mean is equal, let us say, to 6, and then you run, and then automatically must say normal mean is equal to 6. So you must have a title which is dynamic, of course, which is not static. And you see, if the mean is equal to 6, you see that the center of the distribution is 6, of course. Right. Now, here you see the title. If I do not write mean and variance, if I do not put num to str, okay, let us run the file up to this point. You see what you get, density function n nothing. Because if you do something like, let us say, hello, and then this number, this is what you get. This number, for example, is translated into the ASCII code. You see, then it is concatenated with the curly brackets. Do you understand it?
So 1, 2, 3 is calendar.
This one is exactly the char of 1, 2, 3 exactly is the open curly bracket. That's right. So if you do alt 1, 2, 3, you open the curly bracket. If you do volt 1 to 5, volt 1 to 5, you close the curly bracket. And 1 to 6 is the tilde in your keyboard. Right? So, let us say, for example, this one plus 0 is 123, right? So therefore, here when you do hello and then let us say 4, and the ASCII code of 4 is this one, and therefore this is what you get. Therefore you have to convert to string num to str, num to str. So hello, num to str4, hello4, yes. Okay? And this is what you do. Now, have you already seen the comet instead of plot? For example, the comet is exactly equal to plot, but just creates the animation. So you see, the line is animated. Very small thing, however, if you want to be fancy, instead of writing plot, you do. How many? I didn't get it. How many?
The comet is basically not showing only the top value and bottom value.
Yes. First, yes. Right. Right. Here what I've done is I've replaced plot with comet. And here I've replaced plot with comet. So first does the animation for the first subplot, and then the animation for the second subplot. Right, you see. One moment, here. Yeah. And then the second. Then I see that it varies, the speed varies from computer to computer. This is something, yeah. Right. So now we have to do this. We have, for example, write the analytical expression of the probability of x smaller than equal than 1.2. The analytical expression. You want to try to write it down and then we check it. If you have understood. The probability of x smaller or equal than 1.2. I mean, you want to write down the expression. Now, let me do my job from time to time. You know, I grew up teaching this way, and then so it will be the integral from minus infinity to four.
No, minus infinity to plus infinity.
No. You have to find the probability that x is smaller or equal than 1.2. Here there is 1.2. The integral from minus infinity to 1.2 of the normal density with mean 3 and sigma square 4. Okay? So you see. Okay, because so this is, let me see. This is the expression. Do you agree? That's the integral. That's the integral. Right. And how do you compute it? Norm. Which function do you have to use? Of course. 1.2 with mu that is equal to 3, and sigma, not sigma square, sigma which is equal to 2. Right. Because when you say normal, 3, 4 is normal. Mean is equal to 3 and variance is equal to 4. On the other hand, here is parameterized using sigma. Right. So this is the probability. Okay. And the probability of value above 1 minus. Okay. False.
So you can say that minus 1.2 to 1.2 instead of
Right. So if you put minus infinity and plus infinity, here you have is equal to 1. The overall. Now you want to compute the density just up to the value that is requested. Right. Because the overall from minus infinity to plus infinity, the overall area is 1. Okay, now you don't want the overall area, but you want to have the area up to 1.2. Up to 1.2. Whatever. Yeah, does not work. This one does not work. It's the new era where you don't use the blackboard anymore. Okay. Now, now we want to find the probability of having values in the interval 5 and 6, and then we have to shade this area. Okay? It is clear that this is a normal with a mean is equal to 3, and these are the two inflection points at 5, at 1, when the second derivative change sign, you have the inflection point. Okay? You know the mathematics of the inflection points. I hope you do.
understand that we are 5 to 6.
And now we have to find it. That's the purpose of the exercise. Okay, now we have to find this probability, and then we have to color this area. So the integral from here, from 5 to 6 of the density, from 5 to 6, and then you have to find it. But this is the area. The integral from 5 to 6 is this area here. And then you have to find it. Now, let us find it. Norm CDF 632 minus norm PDF 532. Right. Norm CDF, of course. Okay. This is the probability of having values between 5 and 6. Right. Okay. And in fact, you can see from this area that in fact is about 10%, yes, 1/10 roughly. Okay. Now, let us see. Therefore, look at this code. Okay, probability of x smaller than 1.2. Okay, probability of x in between 5 and 6. Okay, you define mu and sigma here. Probability. Let me check. Okay, now plotting probability of x in between 5 and 6. Or you can do it with fill, function fill. Those who want to know more about fill tomorrow will ask me. Okay? Or otherwise, you can do it using norm spec. This is a MATLAB function. Let me see how it works. Norm spec. And then you say, what is the difference that you want to highlight? I want to highlight the interval 5 and 6. Then, for which parameters of mu and sigma? Mean and sigma. And then, here it says, inside or outside. You want to color the inside area, 5 to 6. Yes, automatically colors it, you see. And then this is the probability. Probability between limit is 0.09, you see. Or if instead of doing inside, you do outside, what do you get? You color the complement. Right, well, let me. Okay, you color the complement, okay? Which is about 0. Is that. You color all the area which is outside your interval 5 and 6. For example, you want to color everything which is not in the interval 2, 6, which is not in the interval 2, 6, and here it is. On the other end, if you do inside, it colors this one which is between 2 and 6. Yeah, right. Okay. Now, the quantile. So you wonder, what is let me see. What is write the equation that leaves 2.5% of the probability to the right in this normal distribution. How do you write this integral? How do you write this integral? Now, you want that the result of this integral is what? The result of this integral is 0.975. So you fix the output of the integral, and the output of the integral must be 0.975. What is your unknown here? Given that the output is fixed, what is your unknown? Is the upper extreme. So ft in dt of integral f minus x. X is the unknown. So you must find the x coordinate such that the integral is equal to this prefixed value, which is different from what we saw before. Because before x was given and then you were finding the probability. Now you fix the probability and then you want to find this x. So you see the mathematics. So you see, to find the value, entry 4, right. How do you compute it? So you see, this is the inverse of the function in mathematics. And then it is norm CDF computes the CDF, norm PDF computes the density, norm inv computes the inverse. Norm inv And what is the input of norm-inv? What is the input of norm-inv? The probability. And then here, in fact, it says, look, now the interval is a scalar. Inside 0, 1, you prefix the probability. Okay? Okay, if it is not specified, it assumes what? The standard normal distribution. On the other end, you specify mu and sigma. Mean and sigma. Mean and sigma, right. So 6.9199 is that in a normal distribution, which has a mean is equal to 3 and a variance equal to 4, the value that lives on the right of 6, above 6.9199, there is 0.025 of probability.
So your mean is 3 and sigma is 4, right?
Right.
So why do you initial, how you know that mean is 3 and
Because they are defined here.
Okay.
Yes. Okay, they were defined at the initial, yes, in the initial part of the problem. Yes, I had already defined. Otherwise, you have to put the numbers, of course. Of course. They were, in fact, I defined them once and for all. Right, but of course, that was absolutely a legitimate question. Okay, now you have finally understood that this is the kind of interaction that I want to have. Of course, they have been under my wings, so they know these things very well. I mean, those persons who have already attended the course of me have already been, it is clear that the best students already know these things very, very well. Okay, now let us see. Norm spec. For example, norm spec from minus infinity to 6.9199. Okay, and then you do outside. Right? You see? You see that the probability of having values which are greater than 6.9199 is roughly 0.025, right? And if you do inside, of course, inside you color the other part, and okay, and this probability is 0.975. Once again, you can do with fill. Just for example. No, because we have so many things. Let us compute now the quantiles. The quantiles, these are the quantiles in a standard normal. So I define the quantiles. You see quant names, they become these things here. This is the notation, Z, and then the quantiles. Okay, then norm-inv quant, you compute the quantiles. And then array to table, and then you display them. Okay. So you recognize 1.96, this magic number, That is the probability in the standard normal to have values above 1.96 is 0.025, right? So norm spec of minus 1.96, okay, 0, 1, and then here outside is what? What is this probability? These are the magic. How much? Yes, outside, and therefore what is the probability of having values outside the interval minus 1.96 and 1.9? No, 0.05, 5%, because 0.5 is 50%. Okay? Right? 0.05. That was a missing zero. Okay? Which is very important, a missing zero. Right? And these are the limits of the confidence interval. When you compute the asymptotic version of the confidence interval for the mean of the population. Okay, now, how do you draw numbers from the normal distribution? So again, norm PDF, the density, norm CDF, the CDF, norm inverse, the quantiles, norm RDN, RND, the random numbers. For example. So here in this exercise, suppose that you want to draw numbers. You want to draw numbers from the normal, which has mean mu and sigma is equal to 10. Okay. This function draws numbers from the standard normal. What is the relationship between normal and the standard normal? How do you pass from the normal to the standard normal? If x is a normal distribution, minus mu times sigma is n01. If x is normal, mu sigma squared. Okay, so x minus mu divided by sigma. Therefore, this is called z. If you have z, what do you do to obtain x? Z times sigma plus mu. Right? That's very basic. So numbers from the standard normal times sigma plus mu, and then you obtain numbers from the normal with the mean mu and variance sigma square. Or otherwise, you do it directly. Norm R&D with this mu and sigma and p, and it's exactly the same thing, right? And then this is the assert that all of them are absolutely the same, these two numbers. So you see, numbers from this normal with mean is equal to 6 and variance is equal to 100. So if you compute the arithmetic mean of x, which value do you expect? You expect a value which is closer. But you have generated values which have a true value of mu which is equal to 6. What do you expect? What? No, you expect a sample mean close to 6 mean. Let me run it. And it is called x1. Mean of x1. Mean, okay, because there was this problem that we saw before, that mean was also a variable in the workspace. Now, let me run it, and now do mean of x. You expect a value which is close to 6. The true value of mu was 6, so the sample value is something which is close. Then you remove the seed. If you remove the seed, then here you write mean of x, and this sample mean and sample STD. And for the standard deviation, which value do you expect? Or let us do the variance. Which value do we expect? Or let us do the standard deviation. No, okay. Standard, no, not here. Mean. I want to have the sample mean and the sample standard deviation. Which value do you expect for the sample standard deviation? Don't say anything. Which value do you expect? The true sigma is 10, so you expect a value which is the sample value, which is closer to 10. Let me remove the RNG comment. Sigma, now I have removed the assert because I removed the seed, okay. Let me remove the seed here as well. So you see, this is what you expect for the sample standard deviation. Something which sometimes is greater than 10 and sometimes something which is smaller than 10. Similarly for the arithmetic mean. For the true mean was 6. So the true mean was 6, so the sample mean will be something which is smaller or equal than 6. 5.93, 598. Sometimes it is greater, 6.15. That's the sample variability. Something which is smaller or equal. But the data come from the standard normal, and so this is what you get. Clearly, if you put instead of 10,000, you do 1 million, and then you do the plot, and then the distribution becomes very, very close to the true distribution. Right. Okay. So let us do the summary. So therefore, normal as norm, then PDF, CDF, INV, and R&D, right? Now, the uniform. The uniform distribution is different from the normal. Here in the uniform distribution, the height is constant, does not change in the interval. Right. So here, what is therefore the integral from minus infinity to plus infinity of this area? You see, b minus a times the height, b minus a times 1 divided by b minus a, and so it is 1. Right, you see it? Is a rectangle, and so there is nothing. So let us see uniform. Compute the probability in a uniform 3, 8, and the uniform has two parameters, a and b, which are respectively the lower limit and the upper limit. These are completely different from the parameters of the normal, which were interpretable as the mean and the standard deviation. The uniform, you have to specify what is the lower limit and what is the upper limit. Now, in this random variable, compute the probability of x in the interval 5, 6. Now, what will be this probability? Then, what will be this probability? 3 and 8. The probability of observing values in the interval 5 and 6. What will be? The area that I've shown there, probability of falling inside 5 and 6 is what? Is 1/3, is 1/4, is 1/5 of the total, is 1/6. from 3 to 8 is 5, and here the area is 1/5, and so the probability will be what? No, 0.2. 1 divided by 5. 0.2. 1 divided by 5. Okay? Well, if you don't believe, you do it 1 divided by 5, right? Now, compute this probability and shade this area on the density plot, and then compute the quantiles. Okay. Now, let us do it now. So, you see, do you understand this syntax? That you need CDF instead of norm CDF. Is that the same thing? The only one thing is that UNIF, but then the probability in between 5 and 6. But when you do UNIF CDF, then probability, for example, 6, and then it says enter the value of A, enter the value of B, right? Right, and then A and B, I've defined it here, A and B. So this probability, as you can imagine, is 0.2. Now, let us do the shading. Okay, now this is when you draw the density. Okay. Plot UNIF PDF. You understand UNIF PDF is the PDF of the uniform distribution. You have your x coordinate that subjectively goes from A minus 1 to B plus 1, whatever, because yes, you take the lower and upper extreme of x as you like. And then here you do the shading, or you do the shading with fill, or otherwise you do the shading with this function, distrib spec. This is a function which comes from FSTA. And now, let us try to understand what is MakeDist. Let us see the output, MakeDist. Create a probability distribution object. For example, let us try MakeDist. Okay, so you see that you have all the distributions. You create an object, for example. You create an object, for example, of the uniform. And then it says, what is the lower limit? The lower limit, for example, is 3. What is the upper limit? The upper limit is 8. And so this becomes PD. This is an object. You have created an object which is the uniform distribution. Therefore, if you do plot PD automatically works and gives you this density, plot PD, you see? How it is very easy. So you create this object and then, but this object, like every object, this object has methods and properties. This is the basic thing of the programming languages. The properties of an object represent the data the object contains. For example, let us see. Properties of PD. Okay, these are the properties of this object. So you see, for example, lower, upper. This means that PD dot lower is what? Is 3. PD point upper, and in this case is 8. PD dot distribution name, distribution name, and this is the uniform and everything. Parameter name, parameter description. Let us see parameter description. Okay, lower limit and upper limit of the uniform. Right. Let us do now this thing, and now I do the normal. Normal. With the normal, there is mu and sigma. For example, mu is equal to 3 and sigma is equal to 10 or whatever. Now, plot PD, and then here you have the plot, right, of your normal density. Or now the plot PD, properties dot PD. You see how the properties change dynamically according to the kind of distribution. Before you had A and B, now you have mu and sigma. Parameter description, PD dot parameter description. Location and scale, these are in fact the location and scale parameters. So objects have properties and objects have methods. So the method represents the action the object can perform. Let us see the methods of PD. Methods of PD. Right. So therefore, the mean of PD, and that's the true mean, the variance of PD, right, or the median. So for every distribution, you can immediately have everything, right? So plot PD and then plots these here, the density, everything. And if you create, therefore, an object, and now you can understand this syntax. You create an object of the type uniform with lower and upper, PD. Now you do distribute spec with this object, the interval 5 and 6, and then inside, and then you color it. Okay. Of course, if inside is outside, and then you color the outside part. Okay. The probability of outside is 0.8, the probability of inside was 0.2. Right. The quantiles. What are the quantiles 0.8 and 0.9 in the uniform? Unif inv, right? Then generate random numbers. Once again, if you want to generate numbers which go from 20 to 23, what do? Uniform random numbers, which go from 20 to 23. And then rand creates a number in the interval 0, 1 from the uniform. You want to transform the numbers which are in the interval 0, 1, you want to transform them in the interval 20, 23. What do? Don't say anything, Don't say anything. What do? So you understand the problem. You have uniform numbers which go from 0 to 1. And then you want to transform this number into the new interval 20, 23. What do? So for example, if you have x is equal to rand, for example, 101. X, the mean of x is very close to 0, and the max of x is very close to 1. Right. Now, this number, which go from 0 to 1, if you want to transform them in the interval 20-23, how do you do? Plus
20, minimum plus 20, maximum plus 23.
and so in the code,
Basically, minimum x plus 20.
so if you multiply them by 3, the number go from what to what? They were going from 0 to 1. Now they go from 0 to 3. And to make them go from 20 to 23,
But the internal multiply 0 with
you add the 20.
yeah,
Because first you transform them from 0 to 3. So in general, if you want to transform this interval into this interval, then you do this number times the range plus the lower extreme. Right? These are numbers which go from A to B. Because if you multiply by B minus A, they go from 0 to B minus A. If you add A to B minus A, they go from A. Right, can you get it?
Why doesn't that go from 20 to 21 if the first one was considered?
Because you have multiplied them by 3.
Okay, so we will.
Right. Otherwise, if you do this thing, they go from 20 to 21. So you have this trick that first you multiply by the range, which is 3, and then you add the lower extreme. Right. So here you do with rand or unif R and D is the same thing. Right, and then you check that the two implementations are exactly the same. So you see that the uniform distribution, every interval has the same probability. Right. Okay, now suppose that there is the distribution that you have never heard. For example, the Weibull distribution. The Weibull distribution is used very much in survival time. And you want to see the density. This density depends on two parameters, lambda and k. So this is the density, but however, no one remembers by heart the density. There is no way and no possibility. However, you want to draw this density. This density is just from 0 to plus infinity. Is used to monitor survival time. Right. So here, and you also want to have something which is dynamic. You want to something to do the slider. So you want to change to see how the distribution changes. You want us to do it, or you want us to move forward? So the goal of the exercise is you don't know distribution. However, you create it and then you put sliders in order to show how the distribution changes depending on the change of the parameters. Right? That's the goal. And so, new live script, because we have to introduce the sliders, therefore live script. And then let us put test, and then Weibull effect of the parameters. And then we give title. Okay? Then we have code. These has two parameters. These two parameters of the Weibull distribution are called lambda and k. lambda, we start with the lambda is equal to 2 and k we start with equal to 3. So PD is equal to make this y-ball distribution, then he calls him A and B, but they are called lambda and k. A is equal to lambda and B is equal to k. Plot PD. Let us see it. Okay. Now, lambda becomes a slider. So insert control slider. And the slider is configure control. The slider goes from maybe 0.1 to a maximum, I don't know, of 10 with a step of 0. Then label what the user sees when runs our program. That is the label. So insert the value of lambda, the value of lambda you like. And the default is 2. Then k becomes a slider as well. Configure control, and maybe k goes from a minimum, let us say 0.1 to 6 with a particular step. Okay, and now label. Specify the value of k. Okay, the program has been written. Now, hide code. You see, everything is okay. You see these labels that you just see when you do hide code. Can you see them? Okay. Can you see? Okay. Isn't it amazing that in 10 seconds I've created this program? How long did I take? 5 seconds, 8 seconds? Tell me. Okay? Now, let us stop doing hide code and let us come back. Because now, if you put it on the web, the user sees this, doesn't see your code, and so can play with it. So here you can put in the web the app you like. The user will open your app with all your controls and everything will be fine. You see the power of this thing. Of course, the user, then of course I will be the person that immediately wants to see the code, and the code is just 3 lines. But a person who does not know maybe thinks that this is 100 lines. Of course, if you do it in C++, is 1,000 lines of code. This goes without saying. In MATLAB is 3 lines. You see? Okay. So, is it clear how I did it? Right click, configure control, the label, the minimum, maximum, the step, and the default, run on value changing. So the program must run again every time there is a change in the value of this slider. It is even too easy. Now, take a square random variables. So if you take a series of normal random variables, standard normal, then you square them. And if they are independent, then you get a chi-square. The chi-square depends on a parameter nu, which is called the degrees of freedom. So remember that the mean of the chi-square is v nu or whatever we call it as you like, or the variance of the chi-square is 2 times this parameter. The shape depends on this parameter, and this is the shape depends on this parameter. Shall we do it this plot, or you will do it on your own? Tell me. You think that is something which is really very, very trivial, or we have to do it? What do you think? Or you tell, please go on. This is something which is really very, very basic. I'm available to do whatever you like. The answer is? What is the answer? It is not too trivial. Okay. So here you see that in each panel you must have a dynamic title, right? And then they go from 1 to 20. This window is from 4 and 5. So which subplot is this? This is subplot which has 4, 5, and then this is number 4. This is subplot 4, 5, and number 10, right? Shall we do it with M file or MLX? M. Okay. So therefore, in order to compute the density, what is the function that you have to use? The name of the distribution is chi2, chi-square. Therefore, the function which computes the density, you start writing chi. Chi2 PD, yes, that is automatically, yeah, you start, yes, chi and then ch, chi2 PDF. Okay, here, tell me, the sequence x goes from 0 to 30, right? Right, and then, excuse me, but I've always grown up that a vector is a column vector. I mean, I've always been grown up with linear algebra. If you mention a vector, this must be a column vector. So, chi2 PDF is x and this is y. And then this parameter, okay. You see the artificial intelligence. Okay, is always one step beyond. One step beyond. One step beyond. One step beyond. Key2 PDF. Key2 PDF, but for which degrees of freedom new you want to compute? For example, do new, and then let us say new is equal to 1. Okay? You save it with a particular number, close all, clear all, and then run. Okay? And this is with just 1 degree of freedom. Okay, if we put 20, then we see that the situation changes, I see, depending on this parameter. Now, subplot. Subplot. The grid is 4 times 5, and then I put it, for example, in subplot 3. What does it do here? 4, 5, 3. Which panel of this? 4, 5, 3. It puts the plot in this position, right? Let us see it. Puts the panel in that particular position. Right. Therefore, for J from 1 to 20, because there are 20, now you create the plot in panel J, right? And then you do the subplot, and then you do here new is equal to, these are the title for panel J. Can I write J here? Can I write something like that? For example, of course, this thing here. Now, Control A, Control I in order to format it properly. Right. This, let us try. For J, key 2, 5, let us do right. Here, instead of putting new, what do I put? J, of course. Okay. But what is the problem? See, new is equal to empty. Why? Title, new, what is missing here? What is missing here? New is equal to, tell me? Right, exactly. What we said before, num to str, J. Right. Exactly. Right. Now, you want to write it in LaTeX form. You see, in LaTeX, backslash. And this is the Greek symbol of new. You see the backslash. Probability density. No, maybe let us just put PDF. Okay. Now, let us suppose that we want to do that this 20. Suppose that the user wants to do it just up to 10, or up to 5, or up to 6, right? So if the user does it up to 6, then here it doesn't make sense to create, let me see, just up to 6. You create it just for 6, but it doesn't make sense here. They have to be reshaped, the plot, in such a way that you have 2 times 3. If the user then chooses 10, they might to be reshaped, for example, or 4 times 3, something like that. You want to have something which is dynamic, right? And subplot is not. Subplot is not something which is dynamic. Learn more. Create axis in a title position. Note, tiled layout is recommended over subplot because it enables you to create layouts with adjustable tile spacing. Let us see, tiled layout. For example, let us try to see title layout arrangement. For example, title layout flow. Let us see it. Tile layout flow. Okay. Then here, tile layout flow. Then here I simply put next tile. You see that automatically, that's MATLAB, which is really, really great because next tile. So if you do 1 to 2, then when you run it, it creates 2 panels. If it goes from 1 to 3, then here it creates 3 panels. If it goes from 1 to 4, then it fills all the 4 panels. But if you put 5, what does it do? It automatically creates a layout 3 times 2. And what is amazing is that when you resize it, you see, this is incredible. You have resized it and then automatically the layout has changed. This is something which is amazing, because if you do this and then you do this, you see. This is really the frontier of programming, because I didn't even think that was possible. So it adjusts according to the resize of, right. And of course, if you simply here do figure, then here it creates everything in a new figure. Let us do clear all, close all. For example, from 1 to 15. So you see that it has created 15 figures. And now with the new version of MATLAB, layout, tile all, and then you can see that you can put all of them close to each other. This has come out 2 months ago, 3 months ago. Before it was not possible at all. Right. So, don't you think tab all, tile all? Yes. You do whatever you like. How many lines of code did I write? All is 3 or 4 lines of code. With 4 lines of code, you can do everything. Now let us do, for example, if I generate data, no, it is already 10:20. This means that time passes and then I have to stop. Okay, so we see it again at 10:45.